So having figured out how to reduce the fraction to proper form, now we have to do the second step, which is to factor the denominator. Okay, now remember that the point is we want to factor it into a product of linear and irreducible quadratics. Okay, well, we have a whole bunch of factoring methods, but factoring methods that we know don't always allow us to factor into just linear and irreducible quadratics. Sometimes we end up with difference of cubes or all kinds of expressions like that. Okay, so again, how we're going to do it? What we're going to use is something called the fundamental theorem of algebra. And this is the step which where we're going to find out is that what we want to achieve is possible, but theoretically. And in practice, we have no guarantee that we're going to know how to do it. Okay, so let's see, what does this fundamental theorem of algebra say? You may not have never have heard of this one, okay, but it's a very important theorem, and it tells us exactly what we want to hear. Namely, any polynomial with real coefficients can always be factored into a product of linear and irreducible quadratic factors. Okay, each one of those factors may be repeated. Okay, so what may happen is I start with a polynomial that looks like that, and I can factor it into, well, first of all, there may be a number in front, k0, actually in this case it should be really an, it's the same number. So notice that this an and this k0 are really the same thing. Okay, and then there's going to be some factors which are linear, each one of them raised possibly to some exponents, and then some other factors which are irreducible quadratics, which means if I apply the quadratic formula to each one of those quadratic expressions, I get no solutions. That's what irreducible means. Okay, so again, this theorem tells us that it's always possible to do that, no matter what polynomial you start from. The problem is that unfortunately how to do it in order to arrive at this factorization is not always clear, and in fact sometimes the numbers that we're looking for may be some really weird irrational numbers that that may be pretty much practically impossible to get. But again, it can be done, and that's all we're going to worry about, because in the examples and exercises you're going to do and test questions, it will be doable and doable easily. In fact, in some situation, I will even allow you to skip that step and simply give you the factored form already. Okay, so we're now at the stage where we have factored, well, first of all, we've reduced our fraction to a proper form, then we've factored the denominator into a product of linear and irreducible quadratics, and we want to split the fraction by reversing common denominators. I'm going to show you how to do that through an example, which is a lot easier, just like as I've done so far. And also I'm going to split it into two cases. Notice that in this situation I'm giving you a fraction where the denominator is factored into a product of linear terms only. One of them has power 1, the other one has power 2. Okay, so let's see how that is done. So we want to split that fraction, and so the first thing we're going to do is we're going to consider one fraction for each power of each factor. So we have two factors, x and x minus 2. The factor x only appears 1, we only need one fraction. The power x minus 2 has a power of 2, so it needs two fractions. Okay, and so what the two fractions are going to have respectively in the denominator increasing powers of x, so x of the factor, so x minus 2 and x minus 2 squared. What are we going to put on top? All we need is coefficients. Okay, so we need one coefficient in front of the first, the second, or on top of the first, second, and third fractions. So now notice that if we can actually achieve this split, then we know how to integrate, because the three fractions that you see now on the right hand side are all three fractions that can be integrated using the methods we have. So the only thing we need to find out is how to get a, b, and c. The way we're going to do it is the following. We're going to first of all cross multiply the equation. So in other words, multiply both sides by the common denominator. And if you do that, you end up with this expression. You want to pause and check on your own that this is in fact correct. Now that we have this equation, we want to think back about the fact that we want our new expression to be exactly the same as the old one, totally equivalent, which means that the left and the right hand side have to be equal for any value of x. So what we're going to do is we're going to pick some values of x using some smart values and some easy values. I'll explain in a minute what that means, and use those smart and easy values for x in order to figure out what a, b, and c, the three coefficients we're looking for, are. So let's see how that is done. So first of all, what do I mean by smart values? If you notice the right hand side, there are some values that will make some terms equal to 0. For instance, if I pick x equals 0, the second and third term on the right hand side will both disappear. That makes my calculations easier. Okay? So what I'm going to do is I'm going to set x equals 0, and that gives me that the left hand side becomes a 1, the right hand side simply becomes a 4a, and as a result a ends up being 1/4. So now I found my a. If I went a little bit too fast, you want to pause and check the calculations again on your own. The other smart value I can use is 2, because if I use x equal 2, the first two terms will actually disappear. I'm going to be left with just the last one. So let's do that. If I let x equal to 2, I end up with my equation looking like this. 3 is equal to 2c, therefore c is equal to 3/2. Alright, so I've got A and C already. How about B? Well, I've run out of smart values, right? Only x and x minus 2 were the only two factors. Notice that the smart values are the ones that make one of the factors of the denominator equal to 0. Well, what I'm going to do is I'm going to use some easy values. What can I pick for easy values? Well, first of all, I can pick some small numbers, right? X equal 1 or x equal -1. Or I can pick something that will make one of the other factors be an easy number. For instance, I could pick 3, so that I get 3 minus 2 inside the bracket equal to 1. That's going to be making my calculations easier. And that's in fact what I'm going to use. So I'm going to use x equal 3. And again, if you follow the calculations, that will reduce my equation to 4 equal a plus 3b plus 3c. Well, I know what A and C are, so I can substitute those values in, and now I can solve for B, and now I've got my value for B. So I've got all three of them, so that means that the integral I'm looking for can be written as the integral of, remember 1/4 was the value of A, so that's in front of the integral of 1/x. And then the 3/4 was the value of b, that's going to be in front of the integral of 1/x minus 2. And 3/2 was the value of c, which is going to be in front of 1/x minus 2 squared. Again, these are three integrals that we know how to do, and therefore I'm going to leave it up to you to figure out what the complete answer to this question is. Notice again, this is going to be a fairly lengthy process, right? And lots of little details and so on. So you want to practice enough to make sure that you remember the proper sequence of steps and the proper implementation of each one of those steps, most of which are steps that we haven't normally and commonly done in the course either now or in the previous course. Let's consider now the same procedure, but when we end up with an irreducible quadratic factor in the denominator. Okay? So we're going to do it basically pretty much as before, except that because irreducible quadratic factors don't provide smart values, we're going to have to use more easy values and work with them. Warning, what you're going to see is going to make you probably a little bit depressed because it's a lot of complications, but I'll again, first of all, I assure you that in the test it's the competition are not going to be that difficult, but also there is an easy way to do such calculations more quickly, and I'll mention it. Okay. So first of all, we want to split that fraction. How are we going to split it? Well, pretty much the same as before. So in this case, we have 3 powers. So we're going to need 3 fractions. Okay. But the difference is that on top of the fractions which have the irreducible quadratic in the denominator, it's not enough just to put a coefficient. We have to put a linear function. So we're going to put a coefficient in front on top of x. That's fine. But for the other two, we're going to use 2 linear functions, bx plus c and dx plus f. You may wonder why I didn't write dx plus e. Can you think of what the answer is? I'll leave that to you. I'm sure you'll figure it out. All right. So now we cross multiply the same as before. We're coming up with that. Again, you want to check that the algebra was correct. And now we have to use, well, we have one smart value, right? The smart value x equals 0 is still there. We can still use it. And if we use it, we end up with 4 equals a. right? Which tells us right away that a is equal to 4, so we know that much. But what about the other ones? We have run out already of smart values. We have to use some easy ones. Okay, let's pick some easy ones. First of all, we can pick x equal 1. 1 is always a very easy number. And we come up with that kind of expression from the equation we have. You want to double check it on your own. Now, we know that a is equal to 4, so I can actually rearrange that to read 2b plus c plus d plus f equal negative 11. You can check again the arithmetic on your own. What other easy value am I going to pick? Well, I can pick negative 1, right? That's also fairly easy. And again, I'm going to go fairly quickly through the writing of the equations. You can pause and check it on your own. Again, I know what a is, and I can use the value of a equal 4 to come up with this second equation. Now I can use the next one, which is x equal 2, and I come up with another equation. Bigger numbers, don't panic. Once again, things are not going to be that bad. And then finally, x equal negative 2. Again, if you don't like these numbers, you can pick some other ones. Just pick whichever easy ones you can use. And do the algebra, and we get all this kind of information. All right. So after we've got all this, now we have this information about these coefficients a, b, c, d, and f. The first one is easy, okay? But what about the last 4? Well, what we can do is you can use elimination and substitution, which is the method of solving linear systems that you have seen in high school, or since you're taking the linear algebra course, yes, you can solve that one by Gaussian elimination. Either way, or you can put in your calculator if you have one that does these kind of things. But after you spend about 15 minutes doing it, these are the values that you're going to come up with. And therefore, after you come up with these values, now we can put it together. So we can say that the integral we're looking for is going to be equal to what? A is equal to 4, so a is going to be in front of 1 over x dx. b is negative 4, c is 0. That tells us that we're left with just a negative 4 times x over 1 plus x squared dx. Well, this is something easy to do through substitution. And then d is negative 4, so I can just isolate that one and write negative 4 x over 1 plus x squared squared. Again, this one can be done by substitution. And finally, I'm left with my f that was equal to 1. And that gives me that last integral, which will require a bit more work through an inverse trig substitution. But the point is, we're split it into integrals that we can do using the other methods. Again, notice once again how complicated this thing is. How long, not so much complicated, just long, lots of different steps. Okay? And there is still one missing. Let's have a look at it.